Just to wrap up this last example, we had talked about how to confirm that this point is in fact a maximum. We can't use the d-test here because the d-test assumes there is no constraint. So if we were to just generate points randomly right around the point 10, 20, then these points that are here in this pink color would not make sense because, for example, 20.4 nurses and 10 doctors is over budget. It does not meet our budget constraint. So this equation, if we solve our constraint for y, then at least we could list the values of x that are close to 10, 9.99, 9.9 is a little bit farther away, 10.01 and 10.1 is a little farther away, and then for this point, when x is 9.9 and we plug it into this equation here, we get 20.4 for y. So that's a valid point on that curve. And if we then take 9.9 for x and 20.4 for y, and we put it into our visits equation, we'll get 9,778. Similarly, for x is 9.99, in the constraint equation, in order to meet our $600,000 budget, we would need y to be 20.04. Of course, this doesn't make intuitive practical sense, but it does allow us to verify for each of these points that only the points along the diagonal are valid because these all match the budget constraint. And we see that right around 10 and 20, the most optimal point is, in fact, indeed near the center. It gives us about 9,779 visits. Anything apart from that will give us just slightly less, and therefore we can confirm that 9,779 visits and a little bit more is the best that we can do with the number of visits constraint. So, looking at another example, one that has 3 variables, a company has a production function with 3 inputs, x, y, and z, given by this equation here. Again, another Cobb-Douglas model, but we have 3 inputs, and the output is the level of production this company can make. The total budget is $24,000, and the company can buy X, Y, and Z at $80, $12, and $10 per unit respectively. What combination of inputs will maximize will produce the maximized production? So when we're talking about using the gradient, we know that in order for an optimal value to occur, it must be the case that the gradient value, or the gradient of f, has to be a multiple. The vectors have to point in the same direction as the gradient of g. So we need to compute these things, and we also need g of xy, our constraint, to be constant. Because once again, the total budget being $24,000, we can spend less than that, or equal to that, but we're going to be able to maximize production if we use up our entire budget. So I'll put equal signs here. Now, the next step is to compute the gradient vector of f. And I'm going to go ahead and do that by just taking in it and putting in it the partial derivatives of this function. So with respect to x, the partial with respect to x, the partial with respect to y, and the partial with respect to z are, and again, you could do this with Wolfram alpha, would be 20x to the negative 0.6, y to the 0.2, z to the 0.2. The partial with respect to y will be 10x to the 0.4, y to the negative 0.8, z to the 0.2. And the partial with respect to z will be 10x to the 0.4, y to the 0.2, z to the negative 0.8. And that, remember, has to equal a constant multiple, lambda, times the gradient with respect to g. So the partial with respect to x, the partial with respect to y, and the partial with respect to z. But we haven't written what g is yet. G of x, y, z is the overall expenditure, or the total spent on producing these. So it's 80 per unit of x, but we're going to have x units of it, so 80 times x plus 12 per unit of y times y units plus 10z, and that has to equal 24,000. So when we take the partial of 80x plus 12y plus 10z, we get 80, 12, and 10. And so here we have three equations, one being the 20x, this guy here equals lambda times 80, this guy here equals lambda times 12, and this guy here equals lambda times 10. But we also need our fourth constraint, 80x plus 12y plus 10z equals 24,000. And we'll go over to Wolfram Alpha to do that. When we input our results, here is the whole thing. Again, I'm using L for lambda. Don't forget those because it's easy to forget the L times 80, L times 12, L times 10. And then over here to the right, we have our g of x, y, z equals 24,000. And when we scroll down to find the result, we see that x is 150, y is 500, z is 600. Once again, the value of lambda is valuable, but we're going to ignore it now. And we're going to say that 150, 500, 600 is our critical point. So when we solve this, we can say that 150 and 500 and 600, that combination represents a max. Now, we're not going to go ahead and verify this here, but we're going to assume that because of the fact that as x, y, and z get bigger and bigger, our objective function gets bigger and bigger. So the largest values that we could have to still meet the constraint are these, and that means we should produce 150 units of x, 500 units of y, 600 units of z in order to meet the budget and maximize our overall production, which if we wanted to find out what that is, we could say f of 150, 500, 600 will produce 4,622 units. And that's the most we could produce right there while still meeting our budget constraint. Once again, we could verify this value, but given that it's in 3 dimensions, it would get a little tricky to make this verification. And for all intents and purposes, we're practicing these ideas, and it's okay to stop a little bit short of that process and just acknowledge that this will, in fact, be the maximum that we can do. Any more units, and we'll exceed the budget constraint. Yeah, we'll be able to produce more, but we need to make sure that we do fall within that budget constraint. Finally, we want to take a look at situations where there is no constraint or unconstrained optimization. We can think of this as being our constraint function as being equal to 0, because after all, if g of xy equals c is the constraint, and we let g of xy be 0, then 0 equals 0 is always a true statement. And that doesn't require any limitations on our curve. So if this represents our curve, then if we're just saying that it must be the case that the maximum point lies anywhere along the curve and that 0 equals 0, well, 0 will always equal 0. So when we look at this, our maximum value will be unconstrained in that sense. So we can still solve unconstrained problems in a very similar fashion by utilizing this idea. So a company manufactures 2 items which are sold in 2 separate markets where it has a monopoly. The quantities that you're going to sell Q1 units of product 1, Q2 units of product 2, demanded by consumers, and the prices P1 and P2 of each item are related by this. So the more you produce, if Q1 gets larger, then you're going to have to reduce your price because your supply is excessively large, and so maybe you can't sell close to $600 per unit, but you have to reduce it by some price for every additional unit you manufacture. So for example, if you were to go into a store and look at the number of headphones they have, or for a an iPhone, you're going to find lots of them because you can produce many of them, and when you produce many of them, you're going to have to sell them for relatively cheap because they're in high supply, but maybe not as much of a demand. For product 2, it's going to be the same process, but they're going to be a little bit cheaper, and again, you're going to reduce the price for every additional unit of Q2 you sell. Thus, if the price for either item increases, the demand for it increases. The company's total production cost is given by C equals this function right here. To maximize its profit, how much of each should be produced? So the first thing we want to note is that profit is going to equal your revenue, how much you bring in terms of dollars, but just because you sell something for $30 doesn't mean that that's what you'll be able to take away. You've got to subtract away your cost, how much it cost you to manufacture that. So, for example, if revenue was $30 and your cost was $4, then you actually only made $26 on that product. So our cost function is given by this guy here, C equals, so this is going to be our 16 plus 1.2 Q1 plus 1.5 Q2 plus 0.2 Q1 Q2. And our revenue is going to be generated by how much we sell. Well, we're going to sell each of product 1 for a price of P1. And how many of those are we going to sell? We're going to sell Q1 of them. So our revenue for product 1 is going to be P1, the price of product 1, times how many of them we sell. But we're also going to add to that how much of product 2 we sell. And that product is given by P2 and Q2 respectively. So P2 price times Q2 quantity will give us our revenue, subtract away our cost. So that means our profit function, in other words, the thing that we want to maximize, is going to be equal to all of this. Now, I should be careful here and not say X and Y because my quantities are actually given to me by Q1 and Q2. How much of each product should be produced? Q1, Q2. Now, we assume that P1 and P2 are functions, right? So for P1, we can substitute something in terms of Q1, and for P2, we can substitute something in terms of Q2. So our profit is going to equal our P1, which is 600 minus 0.3 Q1. That's our price times how many of them we sell, plus price number 2, which is for product number 2, which is 500 minus 0.2 Q2 times the quantity. So all I'm doing is substituting P1 and P2, minus 16 minus 1.2 Q1 minus 1.5 Q2 minus 0.2 Q1 Q2. And we're now ready to optimize this. Now remember, we don't have a constraint here. We're just saying maximize the profit. So because there's no constraint on how many we can produce, or at least they don't tell us that, we can say that g of xy equals 0. So in other words, 0 equals 0. So when we set this up, we're going to take our gradient of f, which is going to be the partial derivative with respect to Q1 and with respect to Q2. So if I take the derivative of this thing with respect to Q1 here, I'll have 600 times Q1 minus 0.3 Q1 squared plus 500 Q2 minus 0.2 Q2 squared minus 16 minus 1.2 Q1 minus 1.5 Q2 minus 0.2 Q1 Q2. And the partial derivative with respect to Q1 is going to be 600 minus 0.6 Q1 The derivative of all of these terms up until the 1.2 will be 0, so I'll have minus 1.2. And then my last term